Okay, hi, I'm Eloise Benchley, and I'm going to be giving my presentation on visualizing nuclear spectrums with photomultiplier tubes. Welcome, everyone. Yay. Okay, my advisor is Helen Gaines, who is here. Thank you so much for attending. And yeah, let's begin. So what's the motivation? It's the PF-rich detector. So as you're going to hear a lot about today, there's an electron-proton ion collider being built in Brookhaven National Lab to find out more about the internal structure of atoms. And one of these detectors is the proximity focusing ring imaging Cherenkov detector, which helps you determine post-collision particle mass and therefore velocity based on a momentum measurement you get from other detectors. And this includes high rate picosecond photodetectors, or HRPPDs, which convert and amplify Cherenkov photons, which are formed as energy particles traverse through an aerogel. But part of Yale's job is testing these HRPPDs and the detectors in general, and they need to be tested in a high neutron flux environment that's going to be expected within the EIC. And there is an AutoCAD rendering of what the PF-rich detector is going to look like. So we want to be able, so we're going to obtain an American beryllium neutron source that is made by the following chain to simulate the neutron flux inside of the detector. However, we want to shift the neutron spectrum over the 4 MeV towards 1 MeV by using polyethylene layers to impede the neutrons and slow them down. And so in order to tell that we've been able to shift the spectrum, we need to have a way to visualize the spectrum. So the way we're going to do this is by using scintillators and photomultiplier tubes. And to gain confidence in our ability to recreate the spectrum, we're going to use available beta, gamma, and muons to see that we are confidently able to create the spectrum. So what are, that's a typo, it says should say photomultiplier tubes, but what are photomultiplier tubes? It's kind of an old technology. They are light detectors. However, unlike SiPMs, silicon photomultipliers, they do not suffer damage from radiation, which is nice when you're dealing with radioactive spectrums. They use the photoelectric, they have a photocathode that uses the photoelectric effect to convert photons to electrons. Then across various diodes, there's a secondary cascade that creates a visible signal. For example, and a scintillator converts high energy particles into photons, and it has an emission spectrum, as you can see up there. Oh, I can use the laser up there. And it has a peak emission. And then PMTs have radiant sensitivity to certain wavelengths. So you've got to match a scintillator and a PMT. The gain of a PMT signal is proportional to its supply voltage with an ideal voltage divider, and there can be a linear relationship between, for at least beta absorption, there is a linear relationship between the signal voltage. But so here, let's talk about scintillation, because there's various paths for different particles. So they're all going to come up to here. So I'm just going to go for the first step before they get to here. So with muons, they're heavy and fast, and they have a Coulomb interaction with pi electrons, which results in an electron loss of 2 megaelectron volts per centimeter of the path. So it's basically energy is completely deposited in the path, and it exits the scintillator. Betas scatter within the material, and they are stopped and deposit their entire energy, which means that the energy is quite narrow and precise. Neutrons have an elastic collision with material nucleus, with nuclei within the scintillating material, which results in this neutron scatter. And for hydrogen atoms, the nucleus, which is just a proton, is recoiled, which is a charged particle. So it moves to the next step. The interesting thing is with gammas, there's 2 pathways that are important here. There's photoelectric absorption, which happens where because gammas are a wave, light wave, very high frequency. They're completely absorbed by the material nucleus of the material, and it emits a photoelectron. And the probability of that is proportional around of the effective atomic number to the 5th over the energy. So high density materials and low energy gammas are more likely to be fully absorbed. And then the other method is the inelastic scattering of electrons. It's called Compton scattering, which results in a scattered gamma and a recoil electron. If you know about inelastic scattering, it's dependent upon the angle and just the trajectory of the waves. That means that there's a wide spread of possible values of the energy deposited in this inelastic collision. All of these lead to a charged particle being released within the material, which excites and ionizes the scintillator material. and then the de-excitation of the electron emits photons, and those photons go to the PMT. So those are our methods. So let's talk about the setup. So our goal is to maximize the energy resolution by the full energy, but we have full energy absorption and a high light yield, which results in a very narrow photopeak. So we used a Hamamatsu R182801 PMT, which has low background, high gain, and precise linearity, which is very important for creating a spectrum. We used an EJ200 scintillator, which was actually the available scintillator from the LFH Cal project. It's a very high, fast scintillator. We coupled it to a waveguide with optical matching grease, which makes sure that the diffractive index is the same. And we used Mylar and electrical tape wrapping, which the Mylar makes it reflective on the inside, so it prevents light escape, and the electrical tape prevents light leakage on the inside. And because of the fact that we did this by hand, we have an unknown light collection efficiency, which, if you remember from that equation over there about the signal gain, is a variable. So that makes it harder to precisely calculate the signal that is expected from a particle's energy. So another thing is we used recycled electronics from a different PMT. Part of the way that these tubes work is by having a voltage divider and having proper voltage ratios across the diodes. As you can see here, the voltage ratios for this PMT are different from what we have, which means that we are not getting the same gain that is expected from this. Here are some general stats about just our operating system, and here's a box diagram of the NIM modules that were used to collect the signal before going to the MCA. In order to make it clean, we used a discriminator as well as a shaping amplifier to get to clean as pulse. So let's talk about cosmics. It's expected to be a linear gas distribution around 0.8 MeV because of around a 4 millimeter path length on average through the tile. The tiles are 4 millimeters thick and it's faced towards the sky. So yeah, we were able to use a PSI-PM because it's not suffering from radiation damage. So we were able to make coincidence measurements to ensure that our pulses were actually pulses and not any kind of noise. Actually, the nice thing about cosmics is with different scintillators, we were still able to get the peak. It wasn't really specific to the scintillator that we used. So this one is with the EJ200. You can see it has a very narrow photo peak, which is part of the benefits of the EJ200. This is with a crystal scintillator. It has a wider photo peak, has a bit more noise, but it still works. And another way we can verify our results is with the the number of counts. In general, cosmics tend to hit 1 incident per square centimeter per minute. And that means it's around a 25 square centimeter scintillator, and we ended up with a slightly higher number of 29.5 counts per minute, but that could be attributed to noise. As you can tell up here, there's a little noise area where stuff kind of leaked in. So then we go to our beta detection with something like SR90. The spectrum was produced with an unpollinated 1 microcurie source with the scalar background subtracted. So we did the same exact setup with and without the source, then subtracted it. So we have a clean spectrum, and that produces this. This is the expected spectrum, and that's the decay chain of SR90. Another way to verify our results here was because of the linearity of beta energy deposited in the scintillator and the pulsite, you can use the linearity to predict where the second peak should be based on the first, and it comes within 10 channels on the MCA of the proper peak, which is pretty nice. So unfortunately, we were unable to do anything with a gamma source because our current scintillators are very low density. The density of EJ200 is around 1.05 grams per cubic centimeter, and the effective atomic number is around 5. So that means it's quite low and is very unlikely to fully absorb the rays and produce a clear photo peak. So we ended up not being able to produce it. You might think, oh, there's a peak there. What do you mean? But when you subtract the noise, you just get this plane. That's what's expected with Compton scattering. Right over here is the 180 complete backscatter edge. So that is not a complete spectrum. This tends to be better used for calibration rather than actual, be able to produce a spectrum. Here are for example, here are some crystals that are commonly used for gamma scintillation. They have high density and high effective atomic number, also higher light yield. So in order to produce a gamma spectrum, we have to have one of these crystals. So looking forward, the whole purpose of this was to test it with neutrons. For neutron testing, you usually want a scintillator that contains lithium-6 or boron-10 because they have a large nuclear cross-section. And actually, there is a scintillator called CLYC. I'm not going to tell you what the entire thing is. It's a crystal, whatever, but it's actually a dual mode gamma neutron scintillator with a 307 nanometer emission peak, which means that it would satisfy both creating a gamma spectrum and the neutron spectrum. And it has been shown over here to successfully produce with the PMT and American beryllium spectrum, which we are looking for, as well as the cesium-137 spectrum, which is another gamma spectrum. So yeah, that's all. And I would like to thank my advisor, Helen Kane, Laura Havener, Parker Garg, as well as Paul, who's not here. And yay.
So it looked like a lot of your PMDs respond, right?
Mhm.
What kind of wavelengths do you expect?
Well, you can look at well, its sensitivity rather than, are you talking about in the scintillator or in the PMT sensitivity? Like here. Yeah, well, so this is specific to EJ200. The plot, I didn't include it for the CLCYC crystal, but it has a peak around 370, which means that we might have to switch up the PMT because these are pretty nicely matched with the maximum quantum efficiency of the Hamamatsu PMT. So because the CLCY crystal is around 370 nanometers, we might want to find a PMT that's more sensitive around there. So yeah, that's my answer. I understand the question.
Yeah, I don't have like a good stat. Can you explain me this installation?
Well, so these charts are kind of what scintillation is the general term for high energy particles go in a material and release photons. So these are different methods that different high energy particles in a scintillation in a material produce photons. Yeah, it's a pretty general term, and there's more. This cuts out a lot of steps, but that would take a minute to go through each step. So yeah.